that have done extremely well by changing something inside their economy. And we need to find the secret. And move on to the introduction of probably the first real macro model you've seen with first principles, or microeconomic foundations, as we say. It's kind of an interesting signpost. As undergraduates, you learned about the Solow growth model, and I want to teach you again today that there are limitations to that very, very outstanding piece of academic work. It's still alive and kicking in the economics literature and in the way we teach our students, but it's just the beginning. Okay, and it's the whole purpose of starting with the Solow model is to teach you a lot of ideas and techniques along the way. So today we're going to review what we did last time. I'm going to finish the Solow model and look at some data. I'm going to look at East Germany. I'm going to look at the industrialized countries, the OECD, and I'm going to look at the rest of the world and see how the Solow model fails. I'm also going to talk about what the Solow model has to say about normative questions, like how much should a country save and how much should a country consume. If a country cares about solving some problem like maximize welfare, it could also be welfare net of environmental damage. It doesn't have to be a pure growth story. I think you should all understand that. Economics is much more serious than just growth fetishism. Okay, you just have to put the weights on the relative things you're maximizing. If you want to make the environment clean, you have to spend resources, and resources don't come for free. Okay? And Robert Solow, one of our great scientists who invented the Solow model, actually wrote a very important paper in the 1970s, just after the Club of Rome launched their report, discussing the way you could use the Solow model to think about the environment as a scarce economic resource that gets used up or polluted or whatever. And this model is still being used today. When I finish that, I'm going to talk about one of the most important concepts that will accompany you throughout this year or this semester, and it's called the factor price frontier. So it's a way of thinking about the way factors of production are paid in an economy. Okay, so it's one way of thinking about it. You can also have a Marxist approach to this. You can have a Nash bargaining approach. But the neoclassical approach is kind of the benchmark that everyone should understand before you go around criticizing it. It's a way of understanding what determines wages and profits in an economy. Okay, so that's a really important concept that I learned when I was an undergraduate, but didn't really understand until I went to graduate school. And you have to think and stare at it for a while and understand that it's kind of the basis of everything we do in macro, and also to some extent in microeconomics. Then I'm going to take you into the world of the overlapping generations. So you're all young people, you know older people, you know that you're all coexisting in a very interesting situation where you're about to enter a career and make money, save money, invest money, possibly waste money, and hopefully have a good time on the way. And there are people who are older who are on the way out, have saved during their lives, and have accumulated assets. Some a lot, some fewer. Trying to understand that is a really interesting concept in understanding what the Germans like to call intergenerationelle Gerechtigkeit, Generationsvertrag. All these concepts that the Germans like to talk about actually has an analog or correspondence in economic theory. It goes way back to Maurice Allais in the 1940s. Unfortunately, was recognized too late for this. So Paul Samuelson, as usual, got a lot of credit for it. And we're going to use the Peter Diamond approach to attacking the question of economic growth by explicitly considering capital. So I'll give you a lot of background along the way, and then we'll try to implement a very simple version of that model by the end of the hour, and next time we'll spend more time with it. Okay, so think of the Solow model as laying the groundwork, some important concepts like production function, the savings function, and it's all kind of ad hoc. And the next step would be to use microeconomic theory to motivate why people save and why they dissave over their lifetimes, and what that means for us. This building is amazing. Right? It was built in 1905 by the Berlin Chamber of Commerce. It is capital stock. I mean, it's worth a lot of money. They would love to sell this building to some real estate developer and put people in lofts in this building, right? But it has a certain production possibility, contribution to the production function of Berlin and Germany, and currently it's being used for education. Okay, so it's one way of thinking about who owns this building, what happens when those people are no longer around, it gets passed on to the next generation. It's still there, maybe a little bit run down. That's kind of what's going to drive our thinking when we think about the OLG model, overlapping generations model. Okay? Last week we talked about the Solow growth model, and you've met Andreas. I'm sure he gave you a lot of background on that. He's going to talk to you about it again this week, tomorrow. And it's about a finger exercise. It's a way of understanding everything that's coming. Okay, remember the course is about growth and fluctuations. And to understand growth and fluctuations, as an economist, you have to understand what goes in and what comes out. So the Solow exercise is really an interesting introduction to a lot of interesting concepts that will accompany you for a long time. We start with a closed economy that doesn't have the ability to import capital or savings from other countries. You have to do it yourself. Okay, and this is kind of the benchmark. Think of it as the global approach to economic growth. We have a production function as an abstraction of the relationship between people's effort and capital stock that they use to produce goods and services. And again, this is a very abstract formulation. Think of K as buildings, other structures, cars, trucks, trains, other forms of infrastructure, telecommunications equipment, computers, and lots of machines. Okay, and it has a valuation, and that's what we're going to call K, some constant purchasing power measure of the stuff. And you need to accumulate K. Okay, and A is a variable factor. Okay, A is changing according to technical progress. We're not going to model that in this course, but it's a very important concept. It is basically the wellspring of economic development. The rate of growth of technical progress is the long-run determinant of per capita GDP. Okay, but in the most important part of the Solow exercise is to teach you where K comes from and what makes countries rich or poor. Okay, and we learn that just by staring at the production function. So we're able to infer immediately that there are three sources of a big G, of a big Y, a big GDP. And one of those is just having lots of workers. So it's not surprising that the United States has more GDP than Germany does, because it's just a bigger economy, more people working, more people putting in the labor input. It could also be larger because the United States has more capital. Okay, it's a bigger country. But what really counts is per capita. And that's why we divide by some normalizing factor. It can be the population, it can be the labor input. And for our purposes, we take the labor input just to teach you how to get going with the Solow model. So N equals L to start with. Okay? And finally, technical change. This is the part of the production function is kind of mysterious. It's shifting over time, and it has shifted over the past 250 years. And it continues to shift at different rates of speed. Okay? Over the long haul, it's been about 1.5% per year, 1 to 2% if you like, sometimes speeding up, like in the 1990s when internet was invented and people sort of hooked up. During the industrialization of Germany and the United States, very high rates of technical progress. And then there's periods when it slows down, like the present. And a lot of economists are engaged in trying to figure this out. For the purpose of the Solow model, we assume that it's exogenous. So again, this is a really easy model. You should be able to get your head around this very quickly. A lot of things are just growing by nature. Okay, so the population is growing. The population is equal to the labor force. You know, you can scale it by 60%, nothing happens, as long as that scale doesn't change over time. So again, we're doing things that you need to understand. Economics is about simplifying the world. You know, Einstein said, make your theories as simple as possible, but not too simple. Okay, so it's really a very interesting, it's called Occam's razor, and that's what we're going to be doing for the next couple of hours. Okay, so to review, we had some important concepts. These should all be hardwired now in your head. We have an ad hoc assumption about households' behavior. Households own the companies, so we're also talking by extension about the decision of companies to save. Okay, so the aggregate savings rate is constant. S. It's a parameter that can be changed, and we can look at what happens when the parameter changes, what happens inside the model. Okay, we have a capital accumulation equation. Okay, this is basically an idea of, let's call this capital widening line. This is a situation for equilibrium when capital accumulation is just sufficient to basically take care of the fact that we have growth in population, we have deterioration of the capital stock, that's N and delta, and we also have this notion of increasing effectiveness of labor. So if you want to normalize by effective labor, capital has to keep up with the growth of technical progress. Okay, so to have an equilibrium, we have to be on this capital widening line. That was the ray from the origin in the diagram you'll see in a second. And then we talked about equilibrium in this ky space would be conditions under which little k is constant. Okay, so that's what we're going to talk about, the sort of the Caldor steady state as a way of disciplining our thoughts. So if you think about this equation, this is the so-called Goldsmith equation. It's the change of the capital stock per effective unit of labor is the outcome of gross savings, SY, savings rate times output per effective unit of labor, minus all the capital accumulation you need to do just to keep things standing still. That's the capital widening condition. Okay, so when we have a capital stock that's not changing per effective unit of labor, then the left-hand side of that last equation has to be equal to the right-hand side. Gross accumulation of capital has to be equal to the capital that is sort of being used up just to keep little k constant. Okay, and we talked about that steady state last time. In that steady state, we actually have growth per person, okay, because there's technical progress, and we have growth in GDP because people are also growing. You have more and more people in the economy. So this Solow model has very specific predictions. One is that the output is growing at little a plus n, okay? And those are both exogenous rates. So basically, Solow is going to tell you more about the level of GDP per capita and not the growth rate. Okay, if you want to do growth economics in detail, you need to take Florentina Schwark's course. Do some advertising for a colleague, because that's the big mystery of growth, as Robert Lucas told us, is trying to figure out what determines A over the next 50 years. Okay, but still, we can learn a lot just by staring at this model and get ready for the hard stuff if we want. Okay, labor productivity is growing at this rate of technical progress, which is assumed positive, and it's exogenous. So already these ideas, you can summarize in a very simple diagram, which I tried to get across last time, and Andreas showed you before. The ray from the origin is the capital widening line. The intensive form of the production function is this f of k. And then we have the savings behavior of households and the firms they own. And I say that again because, remember, some firms save a lot, some firms borrow a lot, but they have to borrow from households because it's a closed economy. There's not much you can do. And the government's been shut down in this economy. So we're starting really from scratch. Teaches you where the savings comes from. It has to come from you. Okay, somebody has to be saving out there for an economy to have accretion of the capital stock. Otherwise, it's not going to happen. No gifts in this economy. Okay? So understand this picture, and please understand it well. K star, little k star, is the steady state capital per efficiency unit of labor, and Y star is the output per efficiency unit of labor. That economy is not moving in that picture anymore because we've normalized by the only thing that's growing in the steady state, which is the state of technical progress. Okay? So now the question comes, and this is a great exam question, what happens when one of these parameters that are assumed fixed is changed? What happens if I change the savings rate? Okay, we know that the economy won't grow faster in the long run, but it will grow faster for a while. Okay, and what if the economy stops saving? Okay, what happens if the population growth changes? So we're going to, the interesting question is, what are the dynamics of the economy to the new steady state, and what does the new steady state look like? Okay, we call that comparative statics analysis. Okay, and I had this, again, I'll show you again the same picture. One example, an increase in the savings rate from S1 to S2. So think of Germany going from 25 to 30%. could have many, I mean, if you're a good economist, you can abstract and deduce, think about reasons that could actually have the same implication. The government of Germany wants to have a Schuldenbremse, or the Germans get really scared of the next crisis and start saving spontaneously more money out of their income. These are all possible things we can think of. Or maybe people are living longer and they just want to save more. So anything that would lead to an exogenous change in the savings rate, ceteris paribus, okay, right? Everything else held equal, what happens? Okay, you learned last time, and Andreas probably stressed it, that we move from S1 to S2 means that this old savings function is no longer valid. We have a new savings function. The capital stock is a state variable, so it can't jump. It's actually frozen for the first instant. And the only way it can move to the right is through accumulation. It means that there's going to be some net accretion or increase in the capital stock per capita, per effective unit of labor. Okay, so that new savings point means that we're going to have a distance between this point, the old equilibrium, the old steady state, and this new point, and therefore we're going to have capital formation in excess of that which was the case before. So the consequence of the model says that the economy moves to the right, and it moves to the right until the equilibrium is reached, the steady state condition is reached. This is a very simple dynamic. Okay, so you're moving basically along this this production function from here to here, and you have an increase in y star in the steady state. We'll all be richer. We'll be growing at the same rate, but we'll be richer. We'll have more GDP per capita, more to spread around in whichever way we like. Okay, we can do other types of comparative statics analyses. Okay, so you don't have to be a rocket scientist to see that I can change other things that are exogenous to the model and get endogenous outcomes. And you can use fancy calculus to figure this out. You can also just use a diagram. A good economist should be able to do both. Okay, so we can think about the change in the population growth rate. We can think about a change in the rate of capital depreciation. A lot of people believe now that since we've moved to the digital economy, a lot of the capital we buy, a lot of the algorithms our companies buy and our universities buy, software, computers, have a higher rate of depreciation. That's a fact. But the question is, how much is it? I mean, how much of investment in Germany is actually in the form of software and hardware? Still not very much compared to the buildings that they're building and the factories that they're building. But as we move through time towards a more digital economy, maybe delta will actually be lower or higher, depending on what's going on. I think most people think that in this period of technical change, maybe we're seeing an increase in the rate of capital depreciation. That would have an implication for the model. You can also think about a change in the rate of neutral technical change. Sometimes hard for people to get their heads around, because it's a change in the rate of this stuff that's increasing our wealth, our ability to be wealthy over time in an exogenous way. And you'll see that it leads to some interesting implications about what happens to capital accumulation per effective unit of labor. The problem with the Solow model, and I've said this already, and Andreas will say it again, is that it still lacks microeconomic foundations. So where does S come from? It is a fact that China saves about 40 to 45% of its GDP currently. That's a huge savings rate. Now, is that because the government is telling people to do that? Or is it because Chinese are saving for their children's education? Or they want to save because they're scared that maybe they'll get sick and they'll have to pay for their health care? Okay, these are all reasons that are plausible, but we don't have any really good explanation. Why does America save so little? Is it because Americans are spendthrifts? Or is it because Americans have banks that are trying to milk them of every last bit of extra resources they have by hawking themselves and their students' loans into the future? Or is it something else? Is it just people's behavior, something we can't really explain? So this is kind of where microeconomists have the one-up on macroeconomists. And about 50 years ago, people started to think harder about this and say, okay, we can't do the Keynesian thing and just assume that S is constant, or the Solow thing. We have to actually think about what causes S to be positive. Okay, so we'll get there. Today's objective is to actually move towards thinking harder about some of the microfoundations of models of economic growth. Okay, But before I do that, again, repeat of last time, golden rule. This is an interesting question, and this is also a little sideshow on normative versus positive economics. We all have our opinion about what this country should do, what America should do, but economists should be able to sort out. This is Lionel Robbins in the 1930s writing, economists should know how to sort it out. My opinion, my judgment, my value judgment should be divorced from an objective assessment of what's going to happen or what's driving the situation. Okay, so the Solow model really is a positive model of economic progress, economic prosperity. It's divorced from the fact that maybe the savings rate that that economy has may not be the right one. Might be saving too much. You know, you might just be taking a lot of your income and building machine tools and putting them in your backyard and not using them in an effective way. You might have lots of GDP per capita, but not necessarily very happy. And we know that investment goods don't make us happy, right? What makes us happy is consumption. And consumption doesn't have to mean just getting a beer at the club. It means also being healthy. Consumption is also about having education for your children. Okay, so it's about a lot of things that are not investment, not providing directly for the productive capacity of the future. Okay, so a normative question would not be what is GDP per capita, but rather what should we do? What should we choose? Okay, and you know, we can talk about social planners. There used to be one in this country. In many countries there still are social planner-like agents that actually have a lot of say in how economies choose to invest and save. So what would they do if they had the right to choose? Okay, and then you have to think, what am I trying to maximize? It's a really interesting optimization problem. And this optimization problem is really simple. Okay, what would the social planner do if the social planner just wanted to maximize consumption per capita? Okay, so it's a rarefied, simplified version of a much more complicated problem we'll do in 2 weeks, which is choosing the right path of consumption. Okay, so this is just like choosing the steady state. Right? It's already very interesting, right? Because if you look carefully at this picture, you can see that the red stuff is what makes us happy. The blue stuff is what we utilize to make us happy in the future, in the long run. Because if we don't keep accumulating capital, we're not going to be able to stay there. That's the law of the now invisible capital widening line. I've took it away to emphasize that now the social planner doesn't care about the capital widening line except for the fact it has to be sustainable. So Nachhaltigkeit, right? That's the important thing. It's all about Nachhaltigkeit. How can I sustain this outcome? So if I ask my social planner, maximize the length of that red bar given the constraints of my economy, which are I can't produce more than Y given my capital stock, and I have to get there. So if I want to be over here, I will have to have accumulated a lot of capital. It means I have to save a lot, and I have to save a lot forever. Okay, so if Germany wants to have, you know, buildings like this that are possibly very maintenance intensive on every street in this city, they're going to have to maintain those buildings in the future, and that maintenance is not consumption. And that maintenance in the light of more people is also a factor. So you let in more people, people will put demands on the capital stock, they will reduce the per capita capital stock. And therefore, if you want to keep up with that, you've got to save even more. So it's really common sense. And if you're all sort of looking, wow, that's interesting. It's more than interesting, it's your life, man. I mean, you got to make sure that your rulers or your governors or your politicians choose the right level of savings that gets you to the right point. So now this is kind of the normative question. So Ned Phelps in 1961 wrote a very important paper where he actually tried to ask the question if a social planner could choose a savings policy to maximize the length of that vertical red bar per capita consumption, what would he do? Or what would she do? Okay? It's a woman. And the answer is simple. The answer is unbelievably simple. You set the marginal product of capital per capita to the slope of your resource sustainability constraint, which is the capital widening line. So I didn't do it, I didn't draw it there on purpose, just to make you think a little bit, but if you think about it, we're choosing the level of capital, and that implies a marginal product of capital. That's the marginal extra production that we actually generate when we add a little bit more capital. And if you can just look at the length of that bar, you can see that at some point it's going to be, you're going to be investing so much and saving so much that your requirements on your GDP to be diverted to maintenance of the capital stock will be so high that you won't even be able to have a decent meal. Okay, so the question is, where do I find the maximum? And then you have to set up the maximization problem, which is pretty trivial. Okay, and we'll do it in the section. You set the slope of the production function equal to the slope of the capital widening line. Okay, and remember, in perfect competition, the slope of the production function is something like the marginal product of capital, which is something like the rate at which agents will expect to get compensated for their savings. So in the next step, we'll actually connect that with a savings decision. So it's going to be something like the rate of interest. So if you save too much, interest rates are going to be low, given all your productive capacity. And if you don't save enough, interest rates are going to be high, because an additional unit of capital will have a very high marginal product. Okay? And I wrote here, there are two different types of efficiency you can have. You can think of being on the left-hand side of the optimum, or you can be on the right-hand side. If you're on the right-hand side, that means you're saving too much. It would be possible to increase per capita consumption by unilaterally reducing your savings. Okay, so you've heard there's a lot of discussion in Germany. The Germans are big savers, and they have huge current account surpluses with the world. The current account surplus is kind of a national savings vis-a-vis the rest of the world. So one could actually use this model to make some statement about that. Well, maybe it's because German investment is not productive, and Germans want to take their money abroad. Okay, so that's an extension of the Solow model to an international context. Or maybe the Germans are just over-incentivized to save, or maybe the Germans are just scared and they're just saving like crazy because they're terrified the world is going to fall apart. Okay, so all these possibilities can motivate your thought to think about these things. Okay? So I'm going to finish now about Solow. I'm going to talk about implications for growth, because it's a growth model, but you already figured out that in the steady state, growth is boring. In the steady state, y star is constant, and output is growing at the rate of little a plus little n. And output per capita is growing at little a. Okay, that's all exogenous. So the story of Solow is to teach you how to think about investment and savings, and why countries are richer per capita even if they're all growing at the same rate. So if you look at the OECD, you see the United States and Germany and the UK and France, they're all kind of growing at the same rate over the past 20, 30 years. The US has had a few extra jolts recently. Trump is also kind of a jolt, but over the long run, we know that these rates are kind of similar, but we know also that US GDP per capita is higher and has been persistently higher than in Germany. Okay, part of that is because Americans work more. They work longer hours than Germans do. Okay, more women work in America than in Germany, and they work longer lifetimes. Okay, whether that's good or bad is not clear. Okay, if Americans go on vacation, maybe they'd be happier. Germans have lots of vacation. So all these things have to go into the equation. I'm talking about GDP per capita, so you have to understand that the level is what we're talking about. All right, so you can still have long-run growth, but everyone's kind of, in this model, are growing at the same rate. It's technical progress. But how you get to the higher low could be because you save more. The Germans save a lot. That's why Germany's even richer than it should be if given their labor inputs. And I say that completely without any judgment. I'm just telling you the way it is. And if you compare Germany to France, German GDP per capita is higher than in France right now because the Germans are actually less unemployed than the French are. And if you go to Italy, you see exactly the next level. Okay, or Greece. So these are things that, that fascinate macroeconomists. We're talking about the growth phenomenon. So we're interested in why is changing when it does change. And, we can talk about, when we talk about the comparative statics exercise, we'll have a situation where y star has not yet been achieved. We're either below it or we're above it. So we can describe the process, and actually you can use a little math to figure out what's going on. I'm going to try to motivate this equation, which says basically that the rate of growth, the left-hand side is the rate of growth of per effective capita GDP, is a function of how far you are away from where you're going. Okay? And this is what we call a log linearized approximation to a nonlinear process. So in economics, we use math to help us think about things that are very complicated. And one of the things that's really complicated is that when you're far away from something and you're in a system that's nonlinear, it's very difficult to say very much concrete about the rate of change of being far away. But when you get close, we can make an approximation. So we'll take a first order Taylor approximation of the behavior of the system around the famous Y star, okay? So assuming that's been chosen by the model, we'll get to that in a second. Okay, so we're going to approximate this, and it turns out that you can show that the approximation factor is something we like to call lambda. Lambda is kind of it's not the Lagrange multiplier, it's just it's a function of the model parameters, and it's pretty much set in stone by the model. Okay, so you can actually go out and calculate this thing. This is the share of capital in national income. So 1 minus S sub k is the share of labor in national income. You have the rate of growth of technical progress, you have the rate of growth of population, and you have the rate of depreciation. So I'm going to show you how you can actually get that result. I'm going to motivate what we call log linearization. So Andreas will talk about that. This is a useful tool in economics. You're masters of the universe now. You should be able to think about all these things. Anytime you have a complicated problem, whether you're in micro, public finance, macro, can I approximate around the equilibrium? Actually, you want to ask whether the equilibrium is explosive or not. It's probably not. So to the extent that it's a stable equilibrium, what's the local behavior? And that's what we're going to do with the Solow model right now, just to give you a taste of what is to come. Okay, and all I'm asking you to do is to be able to take derivatives. First order Taylor approximation. And it's a great tool. Engineers use it. Some social engineers use it. Think about the local behavior of viral messages in Facebook. You know, it's very hard to approximate these very nonlinear things, but once you're close to the equilibrium, you can make very, very clear statements. So the way we do this is we take the Goldsmith equation, that's the equation for the capital stock, and then we ask how fast is output changing. Remember, y dot is the derivative with respect to time. That's a standard notation. So the rate of growth of output is always going to be equal locally to the first derivative of the production function times the change in the capital stock. And it's not even it's a fact. So all I need to do is just take this change of the capital stock, which we already know from the Goldsmith equation, and I can plug it in. So I can see that basically if I want to approximate the rate of change or the change in y, and y is not a rate of change yet, it's just the change in y per unit of time as a function of these things on the right-hand side. Okay, it's a function of the capital stock, and it's a function of all my exogenous parameters. So if I approximate that thing, I'm going to learn right away that the change in y per unit of time is driven by the gap between what I'm saving, gross saving, and what I need to stand still, the capital widening condition. Okay, so it's as easy as that. Now, as I said, this is not a rate of change yet. We want the rate of change because rate of change is for economists is great because we don't have to have units, right? If Germany is growing at 2% per year. We don't have to know that Germany's GDP is 3.5 or 3.4 trillion, whatever euros. We just need to know the rate of change. So let's divide both sides by y. So on the left-hand side, we now have a growth rate of per capita or per effective unit of labor GDP. On the right-hand side, we have the same thing as before, except now we're dividing by f of k. So if we knew what the form was of f, we could actually compute that at any point in time. We could compute the convergence speed, but we don't. In fact, we're not we don't have that much hubris that we would say, I know exactly the world is Cobb Douglas, the world is CES. We don't do that. I mean, you do that when you write your academic papers, but I'm trying to speak to students. I'm going to say, look, we're going to be agnostic about it. We have some conditions on the production function, and they've been elucidated already several times, okay? So if you think about it, K is one of the drivers of how fast I'm growing. If I'm very far from my steady state, I'm going to be growing faster. If I'm close, I'm going to slow down. Asymptotically, I'm going to go to 0. Okay, so the question is, how can I approximate this function and make it a function of how far my output is from the steady state? Okay, so all we have to do is effectively invert K, express K as a function of Y, and then go to town. Okay, so the lesson is, if we can do this, I've got my global equation, and I just make an approximation using a first-order Taylor approximation. We call that a log linearization because what I'm going to be doing is I'm going to express this. I mean, this is already like the change of the logarithm of y, because per unit of time. We already said that last time. And on the right-hand side, I'm going to have a distance of the log of y from its steady state. Okay, so even if I don't have an explicit form, as long as I have some weak conditions on the production function, I can invert or express y as a function of k, and k is a function of y, and then I can basically write the following. Y is a function of how far y is from its steady state value relative to where I am right now. Okay, so the approximation looks like this. The rate of growth of y is a linear function. These are all linear because they're evaluated at the steady state of the distance of y from y star. And if you bring y star over here, you can see that's the percentage gap of y from y star. This is a really important implication. This says that the farther I am from my steady state, if we have the same Solow model, that if I'm far away, I should be growing faster. Okay? And if I'm close, I should be slowing down. So if you look at the OECD, this works like a top. I showed you that last time. Okay? But the problem is it doesn't work for African countries. And it doesn't work for all Asian countries. And it seems to work for China because China has done something really special. Okay? And the question is, what is that? That's why growth is so interesting. We have to figure this out. Okay, so let me this is something that we'll do in the section. But if you do the approximation I just discussed, you end up getting this nice formula. Okay, and you can rewrite it. And you end up getting this growth rate of the approximated behavior is a function exclusively of the gap. And this lambda is a function of everything in the model. Okay, so lambda turns out to be a number like 0.04, or if you're lucky, 0.03. That's really slow. Okay, we know from the doubling rule of economic growth and half-lives that if it takes, if this lambda is 0.04, then how many years will it take for us to close half of the gap to the steady state? Okay, 0.04 is like 4%, so take 70 divided by 4, and that's your answer. It's a long time. 4%. And so you're going to see that Barrow-Sali-Martin actually claim that it's 0.02. Okay, so that means that it takes 35 years to close half the gap to the same steady state of your neighbor. Okay, so this is really slow cooking and kind of depressing. Yes, question? That's right. Yeah, I'm going to tell you why. Let me.
My question is, how we can observe the steady state level? I mean, how do we know how far countries?
That's right. That's the problem with the model is you need to have falsifiable predictions. And I'm just showing you one. If we had the same steady state, the model fails. So what do you conclude? Maybe the steady state is different. Maybe the African countries have something else in their production function that makes them less productive, even when they've accumulated everything according to the plan, and they've reached their steady state. They've reached a lower. And I'm going to try to make that point now. I'm Okay, just bear with me. So the point is, this prediction, this so-called convergence rule is the weak spot. It's the weakness of the Solow model. Again, if everyone has the same GDP, the same production function, if everyone has the same savings behavior, if everyone has the same depreciation rate and population growth rate, we should all be converging to the same GDP per capita. That's an unequivocal prediction. And it works for the OECD, okay, but it doesn't seem to work for the poor countries. And economists are actually challenged to explain this. And the good news is that we have countries like India and China and also South Korea that have done extremely well by changing something inside their economy. And we need to find the secret to understanding that, because we still have many countries that have resources. Think of Nigeria, think of several Latin American countries that have not turned the corner. Okay, so the Solow model is stumbling right now. Okay, and the point is that this Y star need not be unconditionally the same. Okay, and the reason we think about this is because Salih, Martin, and Barrow in 1992 actually derived, using my formula, it was their formula, 0.02 for standard models. And if you look for the convergence rate between United States, it's about 0.02, 2% per year. Not income, but GDP. So you can have transfers. West Virginia can get money from the federal government, or California can pay money to the federal government. What matters here is GDP, productive capacity, production per capita. Okay, so the convergence rate is very slow according to the Solow model. And I want you to remember this log linearization technique is the way we get that answer. Okay, for general models, that's all you can do. Now, if you have a Cobb-Douglas setup, you can probably compute the exact rate of convergence, and it's still very slow. Okay? So bad news, OECD seems to work. Countries that were rich at the beginning of this period actually grew more slowly than countries that were poor at the beginning. But if you look at the IMF, all the IMF countries, this is a disaster. It doesn't work. Okay, so back to the drawing board. If we want to use the Solow model to explain economic development, we have to do better than this. So to answer his question, okay, one tweak of the model would be to say that countries have different production functions. It's not just about K and L, it's about other stuff. It's how well your economy is organized, how well educated are your citizens, how much health care do you provide, how much infrastructure do they have, what kind of hospitals do they have, okay? And if you do that, all you do is imply that every country has its own little F. And Germany and France have the same F. Germany and Italy, possibly close. Because it's not just about infrastructure, it's about rule of law. How well are your courts organized? How easy is it to do business? Okay, once you allow that, you can see that you can have the same savings behavior, and yet because you're operating on a different productive possibility, you're going to have less output per capita in the long run. Okay, so this is the saving grace for the Solow model. You need to condition on the other stuff, not just capital and labor, but the things that make the production function more or less efficient, all things given. Not just the growth rate, but also, if you have lots of corruption, if you have to pay everyone when you start a business, what's the point of starting a business? What kind of output are you going to generate? If you can't trust anybody because the courts don't enforce the laws, what can you do? Okay, so that's the fundamental insight of the Solow. It's saving the Solow model. Okay, so now I'm going to try to prove to you that this works for Germany. Okay, so this is my own research. I've been doing research on this for the past 2 or 3 years, actually 5 years now. What is the deal with East Germany? If you look at the data, GDP per capita in East Germany was about 30% of Western German levels in 1992. Okay? Now, everyone says, okay, East Germany, God, they got the West German technology, got the West German infrastructure, schools, rule of law. Surely, Saxony must be able to converge very quickly to the level of Bavaria. Okay? Well, if you look at the data, it ain't so. okay? Standards of living in East Germany are still very high, and they're very high compared to any other the ex-communist economies. We're talking 85 to 95% of GDP of income per capita. But when I talk about production, I'm talking about something else. How much value added is generated on East German territory, okay? Here's the data from the Statistischen Bundesamt. Okay, so this is a time plot of log GDP per capita in all the different Bundesländer. So when you go home tonight, download this and stare at it. At the top is Hamburg. Okay, at the bottom is Mecklenburg-Vorpommern. And you can see that this little band here, looks like electrical cable, is actually East Germany. All the East German Bundesländer, and here's Berlin, and then you've got Schleswig-Holstein and a couple other poor places, and then you're moving up here, you've got Baden-Württemberg and Bayern. So now if you look at income, it's much more converged in Germany because there's a lot of sharing. Germans are very good at that. The Bavarians complain, but they have to fork a lot of money over to East Germany every year, and that's because that's the way a country works. Okay, but the question for me as an economist is why haven't these guys been able to move up to the big leagues? It's like Leipzig making the Bundesliga, why hasn't that happened more often? And the answer must be conditional convergence. There must be something in East Germany, be it the level of managerial talent or regulation, trust among the people who are living there. Something has held East Germany back. One could also say it's because of West German companies. They haven't invested enough. Okay, but that's outside the Solow model. Okay, it is true that there are fewer corporate headquarters in East Germany than there are in West. Big time. Okay, so you might think that's a plot, right? Okay, this is all what the Solow model is about. The Solow model also works for other countries. If you do the conditional story, you can explain countries like Korea, which have a very high level of education per capita. Okay, so that already makes them very productive. They've grown a lot faster than a country like Honduras, which in 1960 had about the same GDP per capita. So the key must be investing in the quality of your labor force. It must also be investing in infrastructure and trying to push beyond the envelope on a lot of other aspects we know have to do with productivity per capita. Okay, so this is a really interesting field. We're going to move away from it now because we've criticized the Solow model because it's ad hoc, but still, it's pretty versatile. It's able to account for a lot of stuff. It doesn't do so well in the global sense if you take it really seriously. So you have to modify the Solow model. It already lacks Microfoundations, so we're already kind of criticizing it. We don't know where this S comes from. We don't know where the other stuff comes from. It's as if you had a planned economy. People choose S, but in fact, the savings rate across countries are pretty stable. So Germany has had a higher savings rate than the United States for about 50 years, just the way it is. Okay, and the German savings rate is higher than that in France, but not as much. And then you have other countries that are, like China, have a very high savings rate, but they haven't really been on the development path that long. 30 years, give them a few years, people will start changing their behavior. Otherwise, we have a problem. Okay? Yeah?
You said that China is saving a lot of money. Is it mostly saved by the government, firms, or by consumers?
It's mostly by households. And the enterprise sector in China is almost, I would think they have pretty much of a deficit right now. They're borrowing a lot, and those savings come from households. But you could go check out the Chinese GDP statistics. You know how to do that, check it. The Chinese government is not running big deficits. It's probably running a small surplus at the time. It's a growing economy, growing very fast. If you're growing a lot, what do you do with the extra 6 or 7, 8% every year? Most people don't know what to do with it. They just put it in the bank. Right? So that's kind of one of the ways of accounting for this. So we need an extended form of the Solow model to account for all this interesting stuff that's going on in the world. Okay, so the Solow model is great. It's a great starter. But we've also seen how the model can be falsified. Right? So the methodology of economics, positive economics, if you like, is to push the model to the limit and see if it matches the data. And if it doesn't, an honest researcher has to say, okay, we have to stop working on this. We have to reject this model. We have to go back to the drawing board. Okay? So I'm done with the Solow model. Abgeschlossen. Now we're going to talk about what people make in this economy. So we talked about East Germany. having lower GDP per capita. But how does East Germany allocate this GDP per capita among the factors that have contributed to producing the GDP? Remember, there are three ways to measure GDP: final expenditures, income, and value added. And they, if done properly, they should all add up to the same number. Okay? So now I'm going to switch gears. We're going to talk about factors of production. Think of the Solow model as just talking about value added. Now we're going to talk about who earns what. And again, we're in a simple model. We have two factors of production. We have capital and labor. So if you own the capital, you're lucky because you can say, well, I earned it, but it's yours. And you use it, and you're not putting any effort. You just own it. That's the way it works in a capitalist society, right? We can try to spread it around. In the model I'm going to talk to you about, everyone has the same access because everyone's the same. But in the real world, we have inequality. We have rich people, poor people. Sometimes you have lots of rich people, and rich people are getting richer. And I'm not going to talk about that right now, but it's important because it also determines people's willingness to play the game. Okay, so all these things are kind of, in a macro sense, important. We're going to start with the simplest. We take the same production function we had before. We have capital and labor. I'm going to set this Harrod-neutral technical progress to 1, so we can just get it out of the way for right now. We'll come back in a second. We'll resuscitate it. So the question is, if we have a market where capital and labor are paid according to competitive conditions. So there's a labor market out there. If labor is scarce, the wage goes up. If labor is in abundance, the wage goes down. And the same is true of capital. What is the compensation we can expect in an economy? Okay, so remember, the way we economists start, we write down some assumptions. So if we're writing down those assumptions, we can actually make some statements about the way factors are paid. And that's going to be very important for us for many different applications. And the neoclassical benchmark is that factors are paid not their average product, they're paid their marginal product. That's because every competitive firm will hire a worker if that worker's extra value to the firm exceeds the cost that the worker has to receive, including Social Security contributions and all the other stuff. Okay? So factor payment equals marginal product. If you accept that, then it also applies to capital, right? Firms will want to hire capital, want to rent cars, rent cranes, rent buildings, if the marginal contribution to the bottom line of doing so is positive. Of course, they have to pay for it. It's not free. So it's a relationship between the two. So using the Solow setup, we can express the marginal product of capital and the marginal product of labor in terms of calculus. The first derivative of the production function with respect to capital is equal to the marginal product of capital. And because we've assumed homogeneity of degree 1, this means that this function is homogeneous of degree 0, which means that I can scale up K and L and I get the same marginal product. All right, that's like magic. That's a fact. It's a mathematical fact. If you allow me to assume constant returns to scale, then the marginal product of those two factors has nothing to do with the size of the economy. So Luxembourg, Germany, US, China, it doesn't matter. What matters is K divided by L. That determines marginal product, not just of capital, but also of labor. Okay, so I can prove that, but you should let that sink in your head, okay? Because it's kind of, you can't argue about it. If you're willing to assume constant returns to scale and competitive remuneration as a benchmark, this is what follows. It's deductive thinking, okay? Now, a good economist would say, well, what if we had monopsonistic employers? What if we had Arbeitgeberverbände that were setting the wage outside the box? Or what if we had unions, okay? These are all tweaks of the model. But right now, this model doesn't have unions, doesn't have employers' associations, okay? So let's do an excursion on this to make sure we're on the same page. The factor price frontier is the way we summarize the possibility that an economy can remunerate its factors according to the competitive standard of wage equals marginal product, rental rate equals marginal product of capital. Okay? In general, this need not be the case. Okay? So if I have a company I could just do whatever I want. I mean, I could try to pay my workers nothing and see if they work for me. I could pay them a lot. I could share everything with my workers. These are two different possibilities. Now, if I do the latter, I may not get anyone to invest in my company. If I do the former, I'm not going to get any workers. So the presumption is that somehow the equilibrium conditions of the economy will guarantee, under conditions of competition, that factors are paid their marginal products. In general, paying factors is a contentious relationship. You just have to read the newspaper, right? We're going to see many strikes coming up this year because workers feel like they're being underpaid. In the United States, it's happening. Minimum wages are rising. Amazon decides to pay its workers more. In the background, you see this thing happening all the time. David Ricardo wrote this. He said, the greater the portion of the result of labor that is given to the laborer, the less there is for profit. It's kind of common sense. And this is the logic of the FPF. Okay? It's a trade-off. You pay workers higher, all things given, competitive remuneration means you have to be paying capital less. Okay? So it's going to be a relationship that has a negative slope throughout, and it's going to be bowed into the origin. It's going to be convex, okay, which any linear combination of the points on the curve is going to be above the curve. It's just a little technicality. It's going to look like this. Okay, so use omega to denote the real wage, and use little r to denote the rental rate for capital. So it's the rate at which I can hire capital from someone who owns it and use it in my production. Now, of course, I could own it myself. It's my own compensation, if you like. Or if I'm a taxi driver and I want to rent the taxi from a company, I'd have to pay R. And we'll talk more about that in a minute. We're going to abstract from depreciation for the time being. Very important. Because obviously the owner of the capital will want to be compensated for the fact that when you drive his taxi or her taxi, you're going to use it up a little bit. Okay, we'll come back to that. So it's easy to derive this formally. It's based on the conditions we've assumed. Okay? So factors are paid their marginal product. Constant returns to scale. Okay, I'm just repeating what I said before. Okay? Because we have constant returns to scale, so-called relationship of Euler, or Euler's relation, says that when you basically scale by some common factor, nothing happens to the marginal product. So if you take Euler's equation, which is this one, output is equal to the marginal output of labor times the labor input plus the marginal output of capital times the capital input, you exhaust GDP. There's nothing left. There's no output left to pay to a third factor. There's no rents in this economy. It's a magic property of constant returns to scale. So if I take this equation and divide left and right by L, I get little y on the left, and I get something that looks like the marginal product of labor on the right plus something times the marginal product of capital on the right. Remember, we already defined this as being, this thing is equal to little k, and f of L is invariant with respect to the size of the economy, so you can rewrite it like this. So basically you write the wage that's payable to capital, to labor, is basically what you have per capita subtracting what you've paid to capital. Okay, so you can think of this as an implicit function. It's an implicit function of R. And you can use calculus to prove that the slope of this curve before, this FPF, is actually equal to the capital-labor ratio. Okay, so this is why we do calculus. Calculus tells us about the slope of curves. And this is an important curve. This says that if I'm in an economy that pays a lot to its workers, I better have, I'm going to have very little left to pay capital owners. And it also says something about the slope of that curve. That curve is going to have a very steep slope, which means the capital-labor ratio is going to be quite high in that economy. Those workers have to earn their wage, okay? Which means you have a lot of capital being put in. Workers are very, very productive. Similarly, if I'm down here, this is all for a common technology. I've set A equals to 1. So if you just do the divide by L and you get this fantastic relationship expressing omega, the wage, as a function of R. And we can actually prove that this is equal to the slope of this function phi is equal to minus little k. Okay, so this is like one of these real like magic wow moments you're going to have. Okay, it's equal the minus k because if we differentiate this function, you basically have three parts. If you just look at that expression, you have three elements of the differentiation. First, you have the first derivative of f with respect to k. Then you have times the response with respect to r, minus k, minus r, minus dk dr. And these first two, this first one and the last one, will be equal if you have marginal product equals the rate of return on capital. So the first and the third terms disappear, and all that's left is little k with a minus sign in front of it. Okay, so no matter what I assume on the production function, that is a consequence. The slope of the production function, the slope of the factor price frontier is negative, and it's equal to minus k. And then to get that result, I need competitive remuneration, constant returns to scale. That's going to be an important building block when we start talking about overlapping generations. This generalizes, okay, so if I let A be non-unitary, what happens if A shifts? We all become more productive. Capital becomes more productive, but especially labor becomes more productive. Labor becomes productive because you're multiplying it by A, but capital is more productive because labor is more productive. Okay, so as long as you have linear homogeneity of the production function, you get the same result. But A will shift the factor price frontier. Okay, so it's the magic of the idea is that if you have technical progress, you can pay workers higher wages without taking anything away from capital, or you can pay capital higher profits without taking anything away from the workers. Okay, so what follows is basically the same proof again, except now the slope is equal to little minus k, where k is now extended to include this a thing, which is no longer equal to 1. Okay, so this device will help us understand that in a modern economy, we observe the rate of return on capital pretty stable. We observe rising wages, capital intensity increasing over time. These are like the magic Caldor facts I talked about last time. Okay, so moving along the factor price frontier is what we're going to talk about now. What happens if somehow I have to pay workers more because of other things these are possibilities. That's why it's called a factor price frontier. It's a set of possibilities, a menu of choices that an economy can pay to its workers and to its firm owners, but it doesn't say which one. It doesn't say who gets what. It just says what is possible. If we're below the frontier, we're obviously inefficient, and if we're over here, we're not obeying the frontier. Okay, so that's only one relationship, and the OLG model that I'm about to show you is a way of connecting the dots. It's a second relationship that will pin down the wage and the rate of return on capital. And we didn't do that with Solow. Solow is it's like a machine. It's like a mechanical sort of a magic black box. This is much more interesting. Okay? So we can basically infer that countries that have high wages with the same technology must be countries that have saved a lot in their past because they've reached this upper left portion of the FPF. And countries that are down here are countries that have kind of missed the boat, even if you've got the technology, you've got the ability, your country has not saved enough. So the savings behavior of households and firms is absolutely essential. And Solow had a mechanical assumption. We're going to do better than that now. Okay? So again, you should be able to understand why the FPF looks like this. You should understand why when we have technical progress, everything shifts out. And if A is increasing secularly, a certain number of percentage points per year, then that FPF will be shifting out over time. And the experience of industrial countries for the past 200 years has been, in fact, exactly that. We have a capital output ratio which is relatively stable. Capital labor ratio has been increasing. But, workers are earning more. Capital rate of profit is pretty much the same. So that's the Caldor fact translated into a modern sort of factor price frontier framework. Okay, any questions about that? Now I'm going to talk about overlapping generations, because the overlapping generations gives us the reason that economies save. Okay, so again, before we were just assuming people have this mechanical, 30% per year of their income goes into savings. We're going to try to do better than that. And that's why we need the overlapping generations model. First step, Now, you're all smart. It's hard to get into this university, so I'm gonna try to make you feel good, because I know you'll understand this stuff. It's really easy, okay? But it's like, again, it's another little crack in the door. I'm gonna get my foot in there. I'm gonna learn more about this stuff. 2 periods, okay? Genius, absolutely ingenious model. Okay, and it was, the first guy who did it was not Paul Samuelson, it was Maurice Allais, French guy. Okay? Unfortunately, he wrote in French, and no one read his stuff. But he did get the Nobel Prize at some point, so it's okay. Right? Sometimes, c'est la vie. I hope no one watches this video in the French-speaking world. Okay? This is an amazing model because it helps us get our hands around things that people are finite-lived. People do not live forever. And if they do, how do they behave? When do they want to save? When do they want to work? When do they want to dissave? Okay? It's a great model for thinking about the price of houses. It's a great model for thinking about asset bubbles. It's a great model for thinking about lots of things. The original concept, after Allais wrote his paper, which nobody read, Paul Samuelson wrote in 1958 about how you could use this to think about money. Think of it as the hot potato theory. It's kind of a cold potato. I mean, I know I can eat the potato. If I wait too long, it's going to go rotten. I'm not going to be around to eat it. So I'm always trying to pass it off to somebody else. Okay, so you can use this model to also think about Bitcoin. You can use to think about cryptocurrencies. You just got to find some sucker who will accept it. Okay, and in this model, they're not suckers. They need it. Okay, so the young people need a vehicle to save, and the old people are willing to pay them for their labor. That's the exchange and the gain from exchange in this model. So it's an incredibly smart model, and that's why we're still using it. There are very fancy models that have been extended with multiple generations, multiple death probabilities and all that kind of stuff. It doesn't really change the fundamental idea. So we're going to consider Peter Diamond, also Nobel Prize laureate, thinking about this with respect to savings and investment. I already said Samuelson thought about it with respect to money. We'll come back to that. Fiat money. The idea is, why do things get accepted that may not have any value intrinsically? Okay, but in this case, in the case of the Diamond's model of capital formation, capital has intrinsic value. It's productive, so it will be worth having. Okay, if you're in the money problem, we'll see later there are some issues about people have to believe that it's going to be accepted in the future. We don't have to believe that the capital stock will be productive. It will be productive. Okay, so I'm going to write down, in the 20 minutes that are at my disposal, I'm going to talk about the assumptions that we need to make the OLG model sing for us, and then we'll possibly get to the first part of the model. But you'll see that the most important thing I've already given you is the FPF. The FPF is one of the scissors, one of the shears of the scissors. The other one is going to be the savings behavior of households. So we need to understand that. We're going to use microeconomics to understand it. Okay, so I'm going to use discrete time. Solow was in continuous time, so now we're going to go to discrete time. Period 1, period 2, period 3, period 4. In any period, this is it, please don't leave. In any period, people live you have two generations alive, only two, old people and young people, because it's really simple. And people have 2 periods on the stage, okay, and they coexist. Young people work, old people eat and watch television, okay, or go to the football games, go to the bar, okay? In that sense, it's a representative household, so everybody has this problem that they know they're going to get old and then retire at some point, and they've got to have something to live off of when they get older. Now you're probably saying, oh, people have children, etc. It's all been done. This model is so amazing that it's inspired thousands of researchers to think about these things. But this is the simple baby version. So you're masters, but you're babies right now. And when you get better at it, you'll be able to manipulate this model like crazy, okay? So every period, you have new people coming on board. They have to work because they have nothing. No bequests, nothing. Then they work, they accumulate, and the second period, they dissave, and they're capitalists. So we've basically solved the Marxian problem. Everyone wants to be a capitalist. Everybody has to be a capitalist. Okay, so again, if you like Marx, we can talk about it. But this is the first cut, understanding the distribution of income and wealth in this situation. Okay, so we're going to assume that agents are actually maximizing their utility. This is a model of perfect foresight, so everybody has an idea of what's going on. They don't have to worry about risk aversion and mutual, diversifying their assets and stuff like that. This is really simple stuff. All that's been done. Time separable utility means that my utility today is independent of my consumption tomorrow. So we're not going to, time separability means the marginal utility of consumption today and tomorrow are kind of independent of the levels of consumption in those two periods. It's just a way of making life simple. It's not that important. What's important is that you have time-consistent preferences. You don't regret something that you decide optimally today, tomorrow. We stick with the production function. Constant returns to scale, and we're going to assume Herod-neutral technical progress. Capital depreciates now. Okay, so if you're a young person, you're going to have to remember that acquiring that capital means that some of that capital in the next period is going to be worth less than it was in the beginning of the first period. And I said that already. So this is a closed economy, no government. Government, you can put it in a second. We will put a government in later in the form of a social security system. Because one of the cool things about this paper is that you only live two periods. You don't care about the children of the children's children in five periods hence. So that has bad consequences. Your behavior has external effects on future generations. And that's why Solow actually used a version of this model to think about the environment. Okay? Because in some sense, we're always passing the environment on to the next generation, and we can schmutz it up a little bit and give it to the next generation and possibly not pay the true social costs of what we did. Okay? So it's a great model. We're going to stick to full employment just to make things simple. Generations are bound together because of the gains from trade. Okay, they gain from trading. When I'm older, I don't have the ability to work anymore, I'm going to starve. And my utility function tells me I'm going to really be willing to pay a lot for consumption in the second period if I can do it. But how do I do it? I have to acquire something that the young people will buy from me, or something I can exchange with them. So the idea would be the young people will acquire my asset, my house, my capital stock, whatever, and use that for their decision problem in the subsequent period. So it's really easy, right? It's easy to understand. It's like an assembly line, right? But the people don't pass each other again, just forever. So the preview of what happens is to think about what is behavior. Each individual, when young, decides how much to work. In this model, we're going to let that person have no decision on how much to work, only going to decide how much to save. So again, this is for you. You can put labor supply in this model as well. The model is extremely generalizable. So we're going to think about goods market clearing. If you save, somebody has to take the savings. Okay, who's going to do that? Okay, again, we're talking about goods. Goods, savings in the form of goods that are not consumed. So when you're older, you'll be able to use your capital stock to trade for output that you can consume. That's the logic. We get rid of government because it's easier, but you can put a government in, there's no problem. But it makes, of course, a difference what the government does. If the government just takes your output and throws it into the ocean, it's going to kind of make you poor. If it makes a bridge out of it, maybe fixes a highway, that's a different story. We're going to talk about when we derive this goods market condition, we're going to look at stability, and I'm going to give you a nice picture. I probably won't finish today, but we'll finish it next time. So here's the notation. Nothing's changed, except now I have to worry about whether you're old or young in period T. Okay, so you have to stretch your mind a little bit. We have two subscripts. The first one is whether you're old, whether you're young. C1 would be the consumption of the young, and C2 is the consumption of the old. The point is you can't all consume. If the young people consume a lot, the old people don't have much. And if the young people consume a little, the old people consume a lot. Okay? But this economy is decentralized, so we're going to let the market decide basically, through its mechanisms, who gets to consume what. What you can choose when you're young is the savings that you put aside. Okay, so you can divide by y and you get a savings rate. It's the same problem. Okay, there's a wage because when you're young you work, and when you're old you get to consume the gross rate of return on the capital, which is the capital less depreciation plus the marginal product of capital. Okay, so you get paid for, think of yourself as you're buying a car. You buy two cars. You buy one car to save into the next period. The other one you use in the current period. Okay, so there's a bit of mental gymnastics. We're talking about output in the most general sense. Okay, output that could be used for consumption or for production. I'm going to assume that agents have a private discount factor that they weight future utility vis-a-vis the current utility. And I'm going to talk about a central planner later. I'm not talking about him now, but this central planner will actually try to do better than the market. The central planner has the ability to, like Wizard of Oz, just move stuff around without telling anybody and try to make people better off. So it's the central planner is like the optimum optimorum, which need not be better than the market equilibrium. Okay, so that's a really important concept we'll come back to. And this is just a footnote. If you do read the Benassi, you can actually weight generations differently. Okay, we'll talk about that. You might really not care about the future. Like, you go figure. Okay, so firms, we've already figured this out. Firms maximize profits. They hire the poor. Marginal product is equal to the cost, the gross cost of capital. There's no depreciation. There's depreciation now, so we have to consider that. The factor of price frontier will deliver us the combinations. So we already know that from just a few minutes ago. Now we're going to try to figure out how savings behavior actually picks off the point that gives us the combination of wage and rate of return on capital that characterizes the equilibrium in this overlapping generations economy. Okay, so let's do it. Savings decisions of the young. Again, when you're young, you write down the plan. I'm going to save this much, and then when I'm old, I'm going to eat it. And I don't have any kids, so no bequest motive. That's it. Okay? So it's going to look like this. Solve this problem. I'm going to choose my consumption when I'm young and my consumption when I'm old, t plus 2. Okay? And what am I maximizing? I'm maximizing the sum of this utility function at different points in time, weighted by beta, which is less than 1. So that expresses my impatience. Okay, so beta is always less than 1. If beta is equal to 0, I'm really impatient. But if beta is equal to 0.99, I really care about my utility when I'm old. So I'm going to put lots of weight on that when I do the right thing. So I want to make this thing as big as possible. U is a concave function of consumption. Okay, so it looks like things that are concave. And it's the same function in both periods. So we've made this very easy for you. Okay, but I can't choose anything that I want. I have to maximize this subject to a in micro, you maximize subject to a budget constraint, right? I want the moon, but I can only have a fraction of it. So what's the budget constraint look like? What I consume in the second period is basically what I saved in the first period times the gross rate of return. Isn't that beautiful? Right? Now we already know that's going to come from, ultimately it's going to come from an economy that's trading, capital and labor. There's the wage. So if I have a high wage, I can consume a lot more in the second period and consume a lot in the first period. But normally if I consume more in the first period, I'm going to have less to consume in the second period. So the budget constraint is a line, okay? It's a line with slope equal to the gross rate of interest. It's the trade-off between consuming today and consuming tomorrow. So this is the microfoundations of the theory. This is a robust implication. People care about the future, but they also have a cost of forsaking consumption today, and that opportunity cost is going to be kind of It's going to be related to my impatience as well as the compensation I get in the market. So the more expensive it is for me, is more expensive to consume today when I have a high rate of interest and a high opportunity cost. When the interest rate is low, then actually I'd much prefer to consume today, all things given. Okay, but also we have to worry about preferences, and that's why we do this problem. Okay, so the agent takes the wage and the interest rate is given, or the rate of return on capital, the rental rate of capital, and the agent has this utility function, which is time separable, and it has positive first derivative, negative second derivative. So it's just a concave function like all the ones you've learned about throughout your life. Okay? So that just makes it interesting for us to smooth consumption. The very robust condition that comes out of this model is that we'd rather have a stable consumption over our lifetimes instead of just going up and down. And that's kind of corresponds to what we observe in people's behavior. People do like to smooth consumption relative to their income. Okay? So that's that's what you gain from having concave utility function like U. Okay? Now, in micro, you'd use a Lagrange multiplier, but I'm going to do you a favor. I'm going to exempt you from the Lagrange multiplier today. Okay? So Lagrange multiplier is just a way of doing what's called constrained optimization. So we want to maximize utility subject to my budget constraint. Well, the cheap way to do this is just to substitute. It's just to solve for one of these variables and plug it into my maximization problem and just eliminate the budget constraint. Okay? So you can do that if you're lucky. Sometimes you're not lucky. In fact, 2 years ago, I had a section leader, Maren Burda. She really insisted on using the Lagrange multiplier, which is fine because you should. I mean, for your life, it's important. But we go slowly here. Okay. So if you do an unconstrained form, you just plug in for C 1t using the budget constraint. Okay. So C1t is actually equal to this. It's the wage, because I'm supplying 1 unit of labor, I get omega, and I can save some of it, I can save all of it. If I save all of it, I'm not going to have very much consumption in the current period, and I'm going to be really desperate. The margin utility of very small levels of consumption is huge, so I can make myself better off by not saving as much. Conversely, I could save nothing and have nothing to eat when I'm old, and then I'm going to be kind of desperate then too. So the idea is to smooth things. Okay? Embedding the budget constraint implicitly in this problem. The solution is the same, so whether you use Lagrange or not, you get the same answer. Okay? Again, repeat. We're trying to derive the right savings decision for this person, given that this person lives 2 periods and faces a market in the second period where he can hive off the capital and she can get something to eat. Okay? So we're eliminating bequest motives. The first order condition, there's just one because we only have one thing you're optimizing. It's my consumption in the second period, or the savings in the first period. Make it even easier for you. Savings in the first period, maximize that, take the first derivative, set it equal to 0, and you've reached the top of the hill. Okay? You've reached the maximum utility for this person. And the first order condition looks like this. Okay, so this is what economics is all about. Marginal thinking. Can I make myself better off than I am right now if I do this? And the answer is no. If I save a little bit more, then I have to put it away and I get it tomorrow or the next when I'm old. Okay, this is what I would give up and this is what I would gain. Because if I give up a little bit of savings, a little bit of consumption today and have a little bit more savings today, I'll get more utility tomorrow, but I'm discounting it by beta, and I'm getting, of course, a rate of return from my investment, from my savings, but it might be very low. If I'm doing the right thing, I've fulfilled this condition, so there should be no gain from doing that. The variational decision, the variational experiment, the mental experiment of just moving consumption back and forth, moving savings back and forth between these 2 periods should yield no additional utility gain. That's what an optimum means. And because the way the model is hardwired, there's only one optimum. Okay? And the second order conditions are fulfilled, and you can actually write it in this very nice intuitive way. Okay, just plugging back C1t into the utility marginal utility of first period, the marginal utility of consumption today is equal to the present discounted value of the marginal utility I get by giving up a unit of consumption and using it, eating it tomorrow in terms of its return. Okay, its return is basically this gross return times the extra kick I get from having that consumption in the second period. Okay, so that's the intuition for the optimum. That's economic thinking. Okay, if we see people deviating from this, we need to ask why are they doing that? Maybe they are, maybe they have good reasons, but the model, assumptions in, result out. So we can use this, and I'll spend more time next week talking about this. We'll finish to use comparative statics analysis. We'll be able to actually use calculus to look at how savings depends on the current wage and how it depends on the rate of return. So this is like the big question in Germany. If you raise interest rates, will people save more or less? Okay? If people get more income, will they save more or less? So this is a perennial favorite. Okay? And the answer is a consumption function defines that relationship. The consumption function or its complement, the savings function, says how much you consume or save. They're not independent. Given income as a function of the wage and the trade-off between current and future consumption. Okay, so I'll finish by writing this function down. This function is really the key to understanding the OLG model, is understanding what makes people save more and what makes people, what is the role of the savings, the return on savings to determining that rate. Because once I've done that, then I'm basically home, because I've already got the factor price frontier. This will determine a second relationship between omega, the wage, and the rate of return on capital, R. When I put that with the factor price frontier, I have an intersection, and that's basically the equilibrium of the OLG model. Okay? So it's easy to show, and this is very intuitive for most of us. If you increase the wage, people will save more. Okay? So if you increase people's income, they save more just because they're trying to smooth. Why should you consume it all today? You're going to consume a little bit today and a little bit more tomorrow. Secondly, the effect of the rate of return on capital is ambiguous. And many of you have taken micro as undergraduates will remember there's an income and there's a substitution effect. If I give you an increased interest rate, you go, well, yeah, great, I got savings, now I'm getting more of a rate of return. Okay, but that assumes basically that you've got savings. There may be a substitution effect where you actually want to consume less today, more tomorrow. So the effect of the interest rate on savings is ambiguous. Higher interest rate means you save less if you're in Germany, because Germans have lots of savings. But if you don't have much savings, if you have lots of debt, it may actually make you less prone to consume. Okay, so ambiguous sign on the effect of the interest rate or the rate of return on capital on savings, but an unambiguous effect on savings behavior. So we've done a lot today, but it's preparation for next time. We talk about how the OLG model works, okay? And we'll talk about the decentralized equilibrium. What happens if you let the market play with itself? And then we'll ask the hard question, what happens if I let a central planner try to do better? Okay? So have a nice week. Don't forget Andrea.